So yeah, so today I'm gonna be talking about what I call like multiscale modeling of OPV devices. So it's putting together a device model that takes into account the main the specific properties of organic solar cells and how like the charge generation process happens in these devices. So my talk will be so my talk will be like in three parts. The first part will be talking about like kind of giving a general introduction of what are the electronic processes in organic solar cells and what are we trying to model. And then I'm going to talk about specifically quantifying and modeling voltage losses in organic solar cells. So focusing on the issue of the high voltage losses and why they're high in organic solar cells. And then how the last part would be talking about how we can put together the this device, like this modeling for the voltage losses together into a device model and try to simulate different experimental results and try and get some information from there. So the first thing is in organic solar cells, so the charge generation process happens through first the absorption of a photon by either the donor or the acceptor that generates excitons. These excitons are strongly bounded, so they need to reach an interface to be able to dissociate. That's why we have like this donor acceptor heterojunction. And so at the interface, we form what we call like the CT state, and like charge transfer state. And from the charge transfer state, we can dissociate, like the charges can be dissociated into free charges that can be transported at the interface and collected. And that's what gives us the short circuit current. From the other side of the spectrum, you have all the losses, all the recombination that happens. So these free charges can either recombine directly through some traps, as in like, or other recombination processes. But in organic solar cells, there's also this main pathway that is going back from free charges to form in this CT state at the interface, and that can recombine to ground either radiativity or non-radiativity, or it sometimes, if the CT state and the LE state are close in energy, we can also see we can also have like going back to the LE state and recombining from there. And these recombination processes is what controls the voltage, or like but what limits our open circuit voltage. And we try to like, so the point is to optimize, like to minimize these to get the highest VUC and therefore the highest PC, whilst not reducing the short circuit current. So for the voltage losses, I'm going to talk first about how we can analyze the voltage losses in a solar cell. So normally we can use the Shockley-Queisser limit. So if we know the band gap of a material, assuming we have like a step-like function for the external quantum efficiency, we can estimate the dark saturation current by multiplying the quantum efficiency by the radiation. So like solar cell that absorbs photon needs to emit due to the reciprocity principle, and that will limit our VUC to this value of VUC SQ that we can calculate. In organic solar cells, it's very hard to quantify this band gap, and we also have, like in real organic solar cell, we often have sub-band gap absorption. So in order to quantify the voltage losses in this case, we introduce this new value that is called, that we call VUC rad. That's like the radiative limit based on the real absorption, or the real EQE that we can measure. So the dotted ones are EQE that we measure for an organic solar cell, and the line here in pink is an extension based on, we kind of use the electroluminescence to extend the EQE based on the reciprocity principle, and that gives us, because we need to have an EQE over several orders of magnitude to get a reliable value for VUC rad. So here we define, like we can define different voltage, like open circuit voltage losses. So one is the difference between the VUC SQ and the VUC rad, that gives us like losses due to the actual absorption profile of the device. And then there is difference between the VUC rad and the VUC, that gives us like the excess losses due to the non-radiative recombination that dominates the recombination process in organic solar cells. So if we do, if we do these calculations for example, a series of 3 different donors where we've modulated their energy levels by fluorinating them, blended with the same acceptor. So here the acceptor is the lowest, like has got the lowest band gap. So the band gap will not be affected, but we're just changing the energy offset between the HOMO and the 2 HOMO levels, or mainly like the energy offset between this CT state and LE state. What we see is that by doing so, we have this luminescence is going to be blue shifted to higher energy. So the luminescence mainly gives is mainly due to recombination from the CT state, and that's why when we change the donor, we end up having a red shift, like a blue shifted EL spectra. And if we do the same analysis for the voltage losses, what we see is that when we reduce the offset, so going from the PBDBT to P4F PBDBT, we reduce that kind of extra absorption losses, and that means that the CT state properties affect these voltage losses, this absorption one. And at the same time, it's been shown in 2017 that the non-radiative part of the voltage losses is also strongly affected by the CT state energy. And in fact, like this, this work by Johannes Bendun showed clearly that there's a strong correlation between CT state energy and delta VNR, and that they could explain this with the energy gap law. And the energy gap law tells you that, so the non-radiative rate between the CT state and the ground state is dominated by the kind of the overlap between the vibronic, like the overlap between vibronic wave function of the ground state and the CT state. And the higher the energy difference between CT and ground state, the lower this overlap would be, and therefore the lower the non-radiative rate constant will be. And that can explain why this delta VNR is dependent on the CT state energy. And they also claim here that the soft nature of this organic molecule limits the voltage loss and gives us like an intrinsic efficiency limit to organic solar cells. But it's like even that intrinsic limit is still quite high. It can go up to like around 20%. So we're still fine to a certain extent. We built on this initial model that Johannes Bendun presented to look at all the parameters of this CT state that can affect the this rates of non-radiative recombination and radiative recombination. And they found like a certain number of properties of the CT state, such as like the difference in Gibbs free, like in energy between CT and ground state, or the oscillator strength of the transitions, how like that would be related to how strongly they absorb light, for example, and also the high frequency and reorganization energy and low frequency reorganization energy. So we put all of those parameters into a model that can calculate, that we can use to calculate the rate of non-radiative decay and radiative decay, and we can use that to estimate the VOC NR based on these. We can also use the same model to estimate the absorption, like the optical response of the system, or like the sub-band gap absorption of the device, and therefore we can estimate the VOC rad as well. So we use that the way we can use this model is, to simulate. We can use this model, for example, to simulate the luminescence of the devices. So here, going back with the same 3 donor polymers blended with here C8-ITEC as an acceptor. And what you can see is that we can use this model to simulate electroluminescence, photoluminescence, and EQE at the same time. And these 3 are simulated using the same set of parameters for both the LE and CT state. And at the same time, we can use this to reproduce the voltage losses and estimate these rates for radiative and non-radiative recombination. So to a certain extent, we can use so using this kind of model, we can make sense of the characterization measurement that we do, and also kind of try and extract the parameters for this CT state that can explain the trend or like the experimental result that we see. And in this case, the only thing that we've changed along this series was just the CT state energy, or like the difference in Gibbs free energy between the CT state and the ground state along the series. So we've kind of assumed that by fluorinating the donor, we reduce that energy, and that would also mean like changing the offset between LE and CT state. And that just changing that parameter, we can reproduce all the data that we can see here. And the observation that we had by doing this is that the device that showed the lowest non-radiative voltage losses, both the non-radiative and like gave the highest VOC at the end, because the VOC rad was also the highest, gave the lowest performance. And that means like that was because the JC was lower as well as the fill factor. So the question was, okay, we can explain the voltage, like the change in the voltage losses in these devices, but how can we relate these properties of the CT and LE state to the device performance overall, like JC and fill factor? And that's when we went to put this voltage model into a model that can simulate the device, and that's what we did here. So the model has got like 3 big parts on it. So one that is related to that like excited state properties that I was talking about, and that would be giving us the absorption and recombination rates for the device, or for like the active layer that we're talking about. And then there is another part that is this like rate model to describe the exciton generation and dissociation based on like, and this kind of model can be used to explain the ultra fast response of the system. And then we incorporate all of this into a drift diffusion model so that we can kind of simulate the response of the system to and a different field, and kind of do the same like kind of simulate exactly the kind of like the JV or other optoelectronic characterization that we can do. The only issue is that with such a model, we end up with a large pool of parameters, and we need to find a way to simulate, or like to kind of if we want to simulate devices, we need to find a way to kind of reduce this parameter and to extract them in a quite a reliable way. And that's the example I'm going to show in the next slides. It's focused on the same like the same series of donor with C8-ITEC acceptor, And here, so we used the steady state EL, PL, and EQ, as well as the voltage losses to get the excited state properties. And now we need to get some properties for the charge generation dynamics, i.e. like this, how fast this exciton dissociates and how fast the CT state dissociates. And then we also need to have some model, like some kind of way to extract the recombination properties. And normally we don't really see the recombination in the ultra-fast time scale, and we can use like optoelectronic measurement, transient optoelectronic measurement in the microsecond time scale to gain some information about the recombination, and therefore extract this reformation rate from this, like the free charges, like electron and hole or CS state to the CT state. And to do that, I'm going to mainly present transient photocharge, which is a technique similar to TPV, but we've showed that it's more reliable to use on low mobility systems such as organic semiconductors. So for the first part, like for the charge generation dynamics, we use transient absorption spectroscopy. And in here, I'm showing the evolution of the absorption in the visible after exciting the donor. And here, what we're gonna try and probe is the ground state bleach of the donor, and that gives us information about how fast the transfer from exciton to CT or CS state happens, and therefore we can extract these parameters. And if we use we use these two parameters, knowing the recombination rates from the previous model to fit the ground state bleach or of the donor. And we can see here that when we reduce the offset, the spectra change significantly, and this can be explained by change in the rates of dissociation of the CT to CS as well as the LE to CT state with change in the offset. So going from high offset to low offset, we reduce this dissociation rate as well as we reduce the recombination rate overall. So now the only parameter that we still need to get is this reformation rate. And to do that, we used the lifetime of the charge carriers to trying to fit the lifetime of the charge carrier using transient photocharge, like extracted using transient photocharge to simulate this under different light intensity. And you can see here that the simulation and the experiments agree quite well. The observation from the experiment was that the high offset system has got like longer lifetime as compared to the low offset systems, and that translated into a reformation rate that is significantly higher for the low offset system as compared to the high offset system. So when we put all of these parameters together, and here I've tried to kind of using this similar donors with the same acceptor, we tried to minimize the number of parameters that could be changing, and we managed to explain different experimental results at different time scales using just 4 parameters that are changing along the series. That is like this reformation rate, the dissociation of CT to CS and dissociation to LE to CT, as well as the free energy of the CT to ground state transition. And when we use these parameters to simulate the devices, we see that there is a good correlation between the experiment and the model, i.e. the JSC is slightly lower for the low offset system. The VOC is significantly higher in the low offset, but the fill factor is much lower than the others. So this way we can kind of explain we can fit, just by fitting other experimental results, manage to reproduce the device performance overall. So the question then is, okay, we managed to do all of this fitting, we managed to do all of this modeling. What can we learn from it, or what's the plus value from having this? So the first thing that we can extract from it is looking at what are the model parameters that strongly impact these, like the device performance, or like JSC, VUC, and fill factor separately. And in our case, we found that, for example, the JSC is mainly related to the ratio of the dissociation rate compared to divided by the recombination rate, whereas the VUC was mainly related to the energy offset, and finally the fill factor was related to this effective recombination rate constant. So we like if then we can use, like, knowing this, we can, for example, focus on how to increase, for example, the JSC. So for example, we could say, like, in the low offset system, if we want to increase its JSC, we could try and increase the ratio of this dissociation ratio, for example. And then the other thing that we can learn from this is also we can use this model to try and infer some relationship between the different parameters, or like properties of the molecules and the parameters of the model. So for example, here, if we compare, we've compared like the ionization potential, which we've measured from APS of the 3 donors, and the difference in free energy, like the difference in energy between the states that we got in the model. And here we found that not only, for example, the offset between LE and CT is affected by this one, is affected by the ionization potential, but also the difference in energy between the CS and CT state are affected by the ionization potential. And obviously that will affect the difference in energy between the LE and CS state. The other thing that we can try and extract from this is looking at how, for example, the rates of dissociation between LE and CT can be affected by this difference in energy between CT and LE. And can we find, and then think about a way to model this this relationship. And here we tried just like a markers like electron transfer rate to try and see, if it fits to a certain extent the relationship between these two. And it seems to be less, like, it's not as it's not very convincing. So there might be something more complicated than that. But for example, if we look at the dissociation between CT and CS in our case, found that using a markers like expression can quite well explain the trend. So we could say that, like, we could to a certain extent say that this CT to CS dissociation rate is, we can explain it by, we can model it with an electron transfer process based on Marcus formulation. And finally, as I said, we can also use this as this model to give guidelines on how to improve the device efficiency, and also how, for example, if we were to increase this dissociation of the CT state, we can increase the JSC of the device, and that would appear as in the ultrafast dynamics as shown here. So going from that low value, that kind of very fast decay at the beginning, to something that doesn't really like the ground state doesn't decay at all. And so that's hopefully, that's it. And I would like to thank all my collaborators and people who have been working with at Imperial and elsewhere, and also the funding for giving us money to do this work. And thank you all for your attention.